Okay, so with this lecture, we're gonna get started on Bernoulli-Euler two-dimensional. Bernoulli-Euler beam column elements. Okay, so we're gonna bring a little bit more mechanics into our structural elements and enable them not only to take axial loads, but take transverse loads, okay, and respond in bending and developing moments at endpoints. Okay. And so if you recall our earlier lectures, early in the semester, right, where we identified what essentially will become a basic system, okay, for the Euler-Bernoulli element. Okay, so you have an element like this, Ij, and the element takes two actions, right? Can develop basically the following forces, just like the truss, right? The element can be in tension or compression, okay? F over bar prime, right? We're gonna call it 3. We'll come back to that point, but I just want to have a good jumping off point for this lecture here, right? Equal and opposite. Right? This is what a truss would do, right? So if f over bar prime 3, you'll see why I'm denoting it by 3 in a second, right? Is positive than the elements in tension and compression, okay? But the element can also develop moments, okay? Like this. Okay. We're gonna call moment at node I, right? We're gonna call this guy F over bar prime 1, okay? So don't be surprised. We're using the notation of the force to denote a moment, okay? And F over bar prime 2, okay? So these are the forces that can develop, okay? At the same time, right, you can develop a rotation that we're gonna call delta over bar prime 1, okay, at node I, delta over bar prime 2 at node J, right? And then corresponding to the basic axial force, remember we have the basic axial displacement that for this case we're going to denote by delta over bar prime 3, okay? And likewise here, right? There's no need for two displacements, you just have one, like in the case of truss. All right, so to summarize, right, basic system. For the truss, right, all we have is F prime 1, which is basic axial force, right? And accordingly, delta over prime 1, which is basic axial displacement, and we talked about this at length. Basic axial displacement. Okay, truss, this is what we studied, old, okay? Now, beam column, okay? You think of it as a truss plus bending action. Okay, or the ability to take transverse loads and respond in bending. bending. Okay? And so in order to accommodate that modeling, right, if you go back to this picture, right, besides just introducing axial forces, right, and axial displacements, we need to introduce end node moments, right, and then the corresponding slopes and rotations. Okay? And so then the basic system for the beam column looks like this. Okay? Rather than one force, we now have three. F over bar prime 1, F over bar prime 2, F over bar prime 3. Okay? The first two will be referred to as the end node moments. Okay? And these are the new guys that you haven't seen yet. Okay? And F3 is your usual axial force. And this is as before. Okay. This is what happens on the force side, right? On the displacement side, right? And so now we call this the vector of generalized forces. Okay, the key word is generalized, meaning that we're generalizing moments, right, to be a type of force. And you need to understand this is a moment, right? But we're kind of putting everything in the same vector and call it a generalized force. And that vector combines end node moments in the first two slots and the axial force in the third slot. Okay. So likewise on the kinematic side, right? We now have delta prime over bar 1, delta prime over bar 2, and delta prime over bar 3. Okay. The first two entries correspond to what? End node slopes or rotations. Okay, we're going to use the word rotations. And these are new. Okay. And this guy is just a basic element, basic axial displacement. And this stuff is as before, old. Okay? And so we've taken basically a truss and upgraded it, okay, to the beam column element by introducing additional degrees of freedom, right? In this case, in the basic system, that correspond to moments and rotations. Okay? And so just like we have a vector of generalized forces, this guy becomes, guess what? Vector of generalized displacements. Okay. Where again we're using the word generalized to lump rotations and displacements into a vector of generalized displacements. We can't call it displacements because rotations are not displacements. Okay. However, the term generalized displacements describes the situation quite well. Okay. So this is our basic system. So now let's begin developing the kinematic relations. Okay? And as before, right, we start with the global element coordinate system. Okay, and we're on page 4.1 of the reader. Okay. Right. So now, as before, we have a fixed coordinate system, xy, okay? But besides xy, we're going to introduce a third axis, okay? We're going to use the right-hand rule, right? Where we line up the palm with the x-axis, curl the palm into y, okay? And the thumb gives us the direction of z, okay? So it's denoted this way. So z in that case, goes out of the page. So in that system, right, we take a structural member, which will now be a beam column, okay? As before, right, it has the beginning node and the end node, ij, nothing changes there. Right? We're going to embed this guy into its local coordinate system denoted by little x and little y, okay? So this is as before. Okay. This guy will have length L, okay? So again, nothing new. All right. This is our angle phi, also as before, right? That the element makes with respect to the global x coordinate line. Okay. The element will have Young's modulus E, area A, right? Length L, and on top of that, remember the inertia tensor, right? Moment of inertia I. That's new. Okay. And just like we have a big Z coordinates, we have little z, defined in the same way, right? You take x, right, curl it into y, and your thumb will point in the direction of z. So we're going to give it the label little z. So at this point, right, the only new thing is the introduction of the third axis here, right, and then the moment of inertia tensor. Okay. Okay. So then, as before, x, y, and now z becomes the global coordinate system. Okay. And little x, little y, and little z becomes the element local coordinate system. Okay. And so basically, if you think of a structural member, right, for example, some kind of like an I-beam, it's, you know, often used in, say, steel construction, right? This guy keeps going. When we talk about the XY plane here, right, or little XY plane, this is really a plane of symmetry, right? So the little x-axis will go this way, the y-axis goes up, right? So this defines a plane of symmetry, right? And that's the plane that we're talking about, right? That passes through the plane of symmetry of the structural member here. So the geometry doesn't change, right? Again, you know, delta x you define as before, x at node j minus x at node I. Delta y you define as before, y at node j minus y at node I. Okay. The length is as before, delta x squared plus delta y squared, right? Using the global coordinates, and cosine phi, or we call C, is delta x over L, and sine phi, or sine S, right, is delta y over L. Okay, using these definitions, using fractions. Okay. All right. So now that we have our geometry set, okay, let's draw an element again, ij. Embed it into a global coordinate system xy. Okay, z comes out this way. Right? And let's define the degrees of freedom. Okay, DOFs. Okay, so what are those? Right, as you would suspect, okay, the node I, just like in a truss, can move in x. Right? So we call it delta 1, x motion, and the corresponding force F1. It can move in y. You get delta 2, F2. Okay? But it can also develop a moment and a rotation. So that rotation in the global coordinate system, I'm going to call delta 3, right? In this two-dimensional setting is counterclockwise, is positive. Okay? And the corresponding moment, I'm going to call F3. So just an expanded definition of the degrees of freedom. Right? I go to node J, I continue, right? Delta 4 is now my new x displacement. F4 is my new x force. Delta 5 is my new y displacement. F5 is my new force, right? And then I can have a moment counterclockwise, right? Delta 6 is the rotation, and F6 is the corresponding moment. And so then, if I write delta now, what I mean is no longer 1 through 4, but 1 through 6. Delta 1, delta 2, delta 3, delta 4, delta 5, and delta 6, like this. Okay. And the global force vector, sorry, element force vector in the global coordinates, now has 6 entries as well. Right? So this guy is 6 by 1. This becomes 6 by 1. And this is F1, F2, F3, F4, F5, and F6. Okay. It becomes 6 by 1. Okay. And so as we go forward, you will see sort of the benefit of doing a very careful job going through trusses first is because, a lot of the concepts will carry over, right? It's just the quantities that we're familiar with in the case of truss will have expanded definition. Okay? Right? So for now, rather than having a force vector of a generalized force vector that includes moments, and rather than having a displacement vector, we can have a generalized displacement that includes rotations. Okay, so now what happens in the local coordinate system? Okay. Local coordinate system and the corresponding DOFs, right? Okay. So this is again same element, node I and J. Okay. Right. This is little x, little y. Okay. And so now, as before, delta prime F1, F prime 1 would be the axial displacement and force at node I. Right. Delta prime 2, F prime 2 will be the y values. Okay. And the corresponding moment and rotation, delta prime 3, F prime 3, will be denoted this way. Okay. So likewise, delta prime 4, F prime 4 is the axial displacement and force. Delta prime 5, F prime 5 is the corresponding vertical case, right, in a local coordinate system. And finally, the rotation and moment are denoted by delta prime 6, F prime 6, like this. Okay. And so now I can say that delta prime vector is a collection of 6 entities: delta prime 1, delta prime 2, delta prime 3, delta prime 4, delta prime 5, and delta prime 6. Okay, a mix of displacements and rotations. And likewise, the corresponding element force vector, right, takes on the following form: F prime 1, F prime 2, F prime 3, F prime 4, F prime 5, and F prime 6. Okay. Basically, we took the old vector of displacements and forces and added 2 rotations and 2 moments. Okay. Conceptually, that's it. Okay. All right. Now, just like in the case of trusses, we want to relate the two, right? So we're working with a basic system, right, with a local system, with a global system. And as you can imagine, the way we're going to build up our analysis framework is we'll start in the basic system, we'll need to convert to local, then we'll need to convert to global. Okay, this will give us a stiffness matrix for the situation, and then that stiffness matrix goes and gets shipped to its global counterpart. Right? All right. So now, what would a relationship be between relation between delta prime and delta, okay? Well, what do we know, right? Let's build it up one by one. Right? So let's see. So we start with delta prime, right? Local vector. Delta prime 2, delta prime 3, delta prime 4, delta prime 5, and delta prime 6, okay? Now I want to express this guy, right? This is a 6 by 1. I want to express this guy by a 6 by 6 matrix. Sorry, right. Times a 6 by 1 vector of the displacements or generalized displacements in the global coordinate system. Delta 1, delta 2, delta 3, delta 4, delta 5, and delta 6. Okay? Good. Right. So next what I'm going to do, right, I'm going to separate the quantities at node I and the quantities at node J like this. Okay? So this gives me a 2 by 2 partition like that of this matrix, right? So now, first we're going to relate, right, displacements, not rotations, but displacements in the local and global coordinate system, right? And those are related in the same way as they are for the truss element. There's no reason why it should be any different, right? So I get a cosine here, I get a sine here, I get a minus sign here, and I get a cosine here. Okay? Right? I go to node J, right? And then I have the same relationship now between the displacements in a two-coordinate system, right? So delta 4 and 5. So I write cosine, sine, minus sine, and cosine. Okay? Now, if I look at this system and I focus on the rotations, okay, here, and the rotation there, okay? All right? Rotations may be thought of as sort of a quantities, right, that point in the direction of the z-axis. The z-axis here and the z-axis there are the same, okay? And so there is no need to have any kind of special relationship between delta 3 prime and delta 3, okay? So I can conclude from this, right, that rotations in the local and in the global coordinate system are the same. Okay? Again, there's no reason to assume otherwise. Okay? So, all right, delta prime 3 equals delta 3. Delta prime 6 equals to delta 6, right? Rotations in local and global coordinate systems are the same. Okay? Right, and so what that does, right, it allows me to put a 1 here, right, and put a 1 there, okay? And then the rest of that matrix just gets populated with zeros, right, because I reflected all the relationships that I wanted to reflect, right? And so the displacements are related to each other through a usual rotation matrix, right, sines and cosines. And then that rotation matrix is expanded to include a 1, okay, for the rotational parts, right? Also, quantities at node I, right, are related with each other. Quantities at node J are related with each other. There's no relationship between the quantities on nodes I and J. So I populate the rest of this matrix with zeros, just like we did for the truss. Okay? And so what you find, right, is now delta prime, right, is related to delta through gamma ROT, okay? And gamma ROT is now expanded to accommodate the presence of rotational degrees of freedom. Subdivided into two parts. Okay. And here you have a cosine, sine 0, minus sine, cosine 0, 0, 0, 1. Then that block repeats. Cosine, sine 0, minus sine, cosine 0, 0, 0, 1. Okay. And there's no relationship between the quantities at nodes I and j, so the off-diagonal blocks are identically 0 as before. So this is your new rotation matrix. Okay. Right. And so without sort of much deliberation or thinking, you can say that the same analysis applies, right, when it comes to forces. Okay. Yeah. And there what you do is you relate the global to the local, just like we did in the case of a truss, right? So let's write down F, okay? F in our case is F1, F2, F3, right? Two forces in a moment, F2 forces in a moment again, right? This is 6 by 1 equals 2, right? Some other 6 by 6 matrix, which I'll build up in a second, right? Times their local counterparts. One prime, F2 prime, F3 prime, F4 prime, F5 prime, F6 prime. Okay. As before, I separate the quantities at nodes I and j, right? Gives me a partitioning of my matrix as follows. Right? And then our reasoning proceeds as follows. Right? First, we relate the force quantities at each one of the nodes. So F1 and F2 to F prime 1, F prime 2. Right? These are related, again, in the same way as the truss forces are related. Right? So I have a cosine here, I have a minus sine here, I have a sine here, I have a cosine here. Okay? Same reasoning goes for the moments, right, as for rotations. So rotations in the global coordinate system and in the local coordinate system are the same, right? And the same goes for the moments. So there's no reason why a relationship like this shouldn't hold, right? Again, no reason to complicate things further. And this, okay, it's the same thing. Right? In that case, I put a 1 here, and I populate the rest of the matrix with zeros. I repeat, minus sine 0, sine cosine 0, 0, 0, 1, right? And quantities from the two nodes are unrelated. So the off-diagonal blocks are 0, okay, right? And what we notice is, even in the expanded version, this becomes gamma ROT transpose, okay? And so we have the exact same relationship as for trusses, right? As for the truss element, as for the truss, right? Where I can take my forces in a global coordinate system for a given element, right? And I relate it to the forces in a local coordinate system by multiplying using a rotation matrix. Gamma ROT with a transpose. Okay. Okay. So far, so good. Okay. Let me stop here. And the next lecture, we're going to continue with rigid body modes. this is where the discussion becomes very interesting. Okay? All right.